2015, day 24. Let's dive in. Okay, it hangs in the balance. It's Christmas Eve and Santa's loading up the sleigh for this year's deliveries. However, there's one small problem. He can't get the sleigh to balance. If it isn't balanced, he can't defy physics, and nobody gets presents this year. No pressure. All right, so what do we have? What are we trying to get? What's the quantum? Okay, so we need a definition of quantum entanglement. Packages need to be split into 3 groups of exactly the same weight. And every package has to fit. First group goes in the passenger compartment. Second and third go in the containers on either side. Only when 3 groups weigh exactly the same amount will the sleigh be able to fly. Defying physics has rules, you know. Okay. First group, the one going in the passenger compartment, needs as few packages as possible. So Santa has legroom. Doesn't matter how many packages are in either of the other 2 groups, so as long as all the groups weigh the same. Okay. Furthermore, if there are multiple ways to arrange the packages, such that few as possible are in the first group, you need to choose the way where the first group has the smallest quantum entanglement. Quantum entanglement, is the product of the weights. Okay. All right, so we have a number of weights. We have to divide them into 3 groups. And we have to make sure the first group has the lowest quantum entanglement. I assume QE here is quantum entanglement. So this one has 99, this one has 90. So this one has the smallest quantum entanglement, but this one has more legroom. Which takes precedence? Oh, if there are multiple ways. Okay, so the legroom overrides quantum entanglement. Of these, although 1091 has the smallest quantum entanglement, the configuration with only 2 packages in the passenger compartment gives Santa the most legroom and wins. All right, so the first thing we'll do is get our puzzle input. Get input 2015, 24. And let's take a look at it. How many packages are in here? Also, not too bad. It's 29 lines. I have to print out the number of lines here. So if we just did it the quote-unquote dumb way, the brute force way, that would be 2 to the 29th different combinations to check, which is a lot. So I don't think, that's what? That's 500 million different combinations. So that's probably not the right approach. So how do we do this? So we do is we can add them all up. Let's see if we could at least do it this way, right? What is this test data? Suppose you have 10 packages with weights 1 through 5 and 7 through 11. In this situation, some of the unique first groups or quantum entanglements are weighted bottom are. Okay. Let's see what we can do here. Let's create our... I should be pretty experienced at this by now, right? Getting everything correct. $23. And then do we have bacon running back here? We don't. Bacon. Okay. Oh. It's better here. Yep. So let's do that. AOC, boom. 2015, day 24. And now we should save it and... Oh, I see. I did get something wrong. After all that. Okay. Good. All right. So right. Let's just create a simple vector with these values. We'll just throw it here in part 1. Let weights is equal to vecbang of 1, 2, 3, 4, 5, and then 7, 8, 9, 10, and 11. So theoretically, we could just run through all the combination. Now with this number of weights, 5 and 5, so it's 2 to the 10. There's only 1,000 to look at. So we could try the combinations. We want to divide them into 3 equal groups, 3 groups of exactly the same weight. So that means there should be a target weight is going to be w.iter.sum I32. Let's just print this out for now. Does that build? Oh, target. 60. So we know that we're looking for a target weight of 60 for this test data. We could run through the combinations, right? We have the combination thing we did a while back, aoclib combinations. And we can just say for combo in w.combinations. And then we can add up and see if it matches the target, right? Let sum equal combo dot, and combo is an array, yeah, vec of I32. So we can just say combo iter sum, do it that way. If sum is equal to the target, then let's just print out this combination. There won't be that many, right? Combo. Let's see what that looks like. Oh, divided by 3, right? Okay, so there's a bunch of different combinations, and we can actually see it here, right? 911, there should be a 1091, 1082, and so on. And so there's a bunch of different ones. He's not showing all of them, he's just showing some of them. That's fine. So we could just use this to calculate the lowest quantum entanglement. The problem is, like I said, you know, this was 10 numbers. So 2 to the 10th different combinations, which is 1,000 approximately. The other one's 29 numbers, which is 2 to the 29th, which is half of 2 to the 30th, and I know 2 to the 30th is a billion numbers. So I don't want to go through a billion different combinations. So I think what we want to do is just search for, we can check an array of, oh, you know what we did? Let's go back to our combos code, because this was key before. We can generate every different combination using this code. But what we've lost when we converted over to this version of the combinations code was the ability to specify how many entries you wanted in the combination, whereas the other version could do that. Let's take a look at that. General purpose combinations iterator. It was, yeah. So we were able to say, you know, how many different items in a particular combination. And then I just incremented that each time through the loop. So the first time we would generate all combinations of 1, then all combinations of 2, then all 3, and so on. And I think that's what we want to do here, right? We want to just say, give me all combinations of 1, and does that sum to the target? Because the first key is fewest number of packages. So if we can add up all the combinations of 1, which it won't be the target, right? Because the biggest was just in the hundreds. Let's just cat this out. Yeah. So I don't know what the sum of all these numbers are. And then we can actually find out. Let's do that real quick. What's the sum of all these numbers? This is our test code. All I want to do is say let input sum equals aoclib read lines input 2015-24.text dot, and that's a vector. So iter parse I32 unwrap. Oh, we have to map it to a parse. Iter map x dot parse I32 unwrap, and then we can sum it. And that should also be an I32, and then we can say println input data target is sum is equal to input sum. Let's see what that sums up to. 1560. So 1560 divided by 3 is 512. No, 520. Sorry, why did I say 512? 520. Okay. So we're going to need more than one, right? That was the whole point of doing this, is say, okay, we're going to need more than one entry. So we could start with the combinations of 2 and 3 and so on. So I think what I want to do is revive this code, but call it something else, right? We have pub-trait combinations. We can grab this. Is there a way to get the raw version of this? View file. And then I can say raw, right? Yeah, here it is. So we have the combinations version, and then I want to create, oh, this is test code. And then I want to create pub trait, what should we call it? Combinations of T. Right, and then self. Combinations of iterator T. And then we're going to impl T clone. Oops. Combinations of T. I guess I could just copy paste for vec T. Fn combinations of self. Combination of iterator T. Combinations of iterator new self. All right, and then we have this. So all of this just copy paste. Oh, except we don't want a loop of on the combos. So we'll fix that in a second. Copy, paste. So, and these have to get renamed. Oh, I missed the beginning of this struct. How did I do that? There we go. This is combinations of iterator. And all these stay the same. Combinations of iterator. And now we're going to pass in the combo, right? Because we want to specify how many, and it's a U size, so we'll just say combo here. How many entries from the vector we want combinations of. And then this, we're going to get rid of the loop, because we're not going to increment combinations down here. So this goes away. Let me reformat that. Everything else stays the same, right? Is there anything we need to change? We just never have to increment combo. Does this even build? No. Oh, I forgot to change this. Of. Did I typo this? Supplied one argument. Oh, I got to pass in, right. Combos usize, combos. And this also needs a combos usize. And it still doesn't like this. Expected option vec T. And what am I doing here? Oh, I forgot to put a none. After we're done with this loop, we say none. All right, because we're going to return the combos until we can, and then we just return none. Yeah. All right, let's see if this works. If this works, this is going to be a very quick day 24. Oh, well, we haven't seen part 2 yet. We're going to look for the thing with the smallest weight. Let's use the test data. Let's just do this for now. Make this thing here, and then instead of combinations, we can say combinations of. Right, so we're going to say for n in 1 dot dot w dot len, and this will be combinations of n. And then we check the sum, and if it's equal to the target, then we'll print that out. But once we've found one, we know the size that we're looking for. So we can say let done equals false if done, if done break, and then here we're going to set done to true. Combinations of. Okay, so it only found one of that size that matches the target size. So that's right. It stopped after that. So let's see if we get rid of this W business and change this to input. Oh. Now we want to input vec. Let's just call it gifts. And now instead of summing it, we'll just do that. Vec I32 and then dot collect. All right, there we go. Now we're not using combinations of, and we don't have W. So now we say gifts iter sum divided by 3. And here instead of wlen, it's gifts.len. We're still not using gifts. Okay, so there's a whole bunch of, we can see, and they're all 6 long. Yeah, and then part 1 is 520. That was the division by 3. Okay. So each one of these is a possibility. So we just need to find the one with the lowest quantum entanglement. That seems straightforward. Let quantum entanglement equals QE equals 0. We don't need to print this now. We just need to say if QE is equal to or sum, no, product. We're looking for the product now. So, because that's a quantum entanglement. So let prod I32 is equal to combo iter product. Is it product or prod? I can never remember. If prod is less than QE, then we're going to save this combination. All we care about is the QE, right? That's all we care about for the result is what's the quantum entanglement of the first group. So we just say QE equals prod. I can't use max because I'm using 0 to indicate we need to set it. Well, I guess I could say this, right? I32 max. And then we can just say QE equals QE.max, min, right? We're looking for the lowest quantum entanglement, like that. And then done is true. And instead of target, we want to print out QE. I missed a semi there. And what does bacon tell us? Ooh, attempt to multiply with overflow. Okay, so maybe I32 is not the right number. Let's try changing I32 to I64 and see if that gets us anything better. We got a number. What do we say we give it a shot? Yeah, that's the right answer. And we didn't even have to, I was thinking maybe as a trick we would have to check to make sure that you could use the remaining gifts to balance evenly. Maybe there's a combination where you come up with a set of gifts that fit in the middle compartment, but then the remaining gifts can't be evenly divided between left and right. But apparently that's not the case, at least in part 1. Maybe part 2 will have that. Okay, yeah, let's save this. Git status. I want to actually git add input, git commit dash m, day, oh yeah, 2015, day 24 input. Do that as a separate commit. And then, oops, and now I've forgotten. It was just combo. I wanted to do combo separately. Git add source combo, git commit, add a combinations of to get a specific number of entries in the result back. And then git add source, git commit dash m, 2015, day 24, part 1. All right, let's move on to part 2. Part 2, that's weird, the sleigh still isn't balancing. Ho ho ho, Santa muses to himself, I forgot the trunk. Balance the sleigh again, but this time separate the packages into 4 groups instead of 3. Isn't that just dividing the target by 4? I'm confused. That doesn't seem like it's particularly difficult. Let's do this then. Since I did this in the parse thing, I mean, did this in part 1 and it should be part of parse. Let's say self.gifts is equal to, and then add this here. Gifts is a vec I64, and this should still work, except now I have to put self gifts. Oh yeah, gifts vec. Yeah. Okay, and we still get the same answer. That looks right. Yep, okay. So now I should be able to refactor this out into a separate function. So impl AOC 2015. Oh, we already have that up here. Let's put it here and then just say fun divide QE of division. And let's just make the divisor I64 and it returns a quantum entanglement. So instead of saying if done break, we say if done return QE. Otherwise return 0 for failure. Maybe -1 for failure. And then we just divide by divisor. And then we just change this to be self.QE of division 3. Wow. There we go. How did I flip around the D and the... Okay, we messed up something here. This function doesn't have a self parameter. That's true. It does not. Okay, and we got the same number. I mean, that looks the same. Yep, 3891, 3891. Good. So and then this one is just this. We'll change that to a 4. And see if that's working. That's the right answer. There you go. Okay, so by solving it this way, it made part 2 really, really straightforward. A lot more straightforward than I thought it would be. Is there anything we can do to clean this up? I don't think so. How long did it take to run? Oh, this part 1 took almost a second. And then part 2 went a lot faster. I've seen that before with these solutions. I think day 22 had similar kind of imbalance. Even though it's running this is running the same code. Maybe with this you need fewer combos. You don't have to go as far to search for a target sum. I don't know. Anyway, git diff. What do? We refactored everything. That's most of the work was refactoring, and then all we did was add this one line to get the solution. Yeah, that looks good. I like it. Git commit -am 2015 day 24 part 2 done. Oh, okay. We can fix that. 32. Oh, maybe we return an option. Maybe that's a more rusty way to do it, right? Because if we can't find one, we should just return none. So this should be a sum. And this is none. And then down here we say unwrap. Oops. Ravind, thank you for the follow. Very much appreciated. If you want to chat, just let me know if you've done Advent of Code as well. It's a fun little puzzle website. All right, so this should run exactly the same, and it does, right? And then Clippy should be happy. Good. And then let's try this again. There we go. Okay. Return to your Advent calendar. So now we have just this one day left. And like I said, the day 25 is usually pretty straightforward because part 2 of day 25 is do all the other previous 24 days.